Okay, welcome back. We have just started talking about taking derivatives, which is, one of the biggest concepts that we do in calculus. And now we're going to kind of look at that a little bit more, but specifically what it means for something to actually have a derivative. The fancy word for that is differentiability. Okay, and we say that a function is not differentiable at points where f prime of x doesn't exist. Okay, so again, differentiable or differentiability, that's just a fancy way of saying there's no derivative at this location. Okay, and there's some obvious times when it won't make sense to do a tangent line, right? Because that's what the derivative is. It tells you the slope of a tangent line. There's going to be some obvious times where you can't. And then there's going to be some times where it's not so obvious. The obvious cases are basically where we have discontinuities, right? And so if we have a hole, then there's no derivative at that location. If we have an asymptote, okay, then we have no derivative. Or if we have a jump discontinuity. Okay, all three of those, okay, mean that the function at that location is not differentiable. Now, the ones that are a little less obvious are the ones where we have continuous functions, but the derivative still doesn't exist. And so let's kind of elaborate on this. Okay, so here are three basic scenarios where that could be a thing. Number one, if we have corners in the graph. And so here's the most basic graph with corners. Let's say the function f of x is just the absolute value of x, right? Well, if we look at the graph, right, we know the graph looks something like this, okay? And so now keep in mind, we see absolute value of x. What that really means, if we're using the definition, is that we have x if x is greater or equal to 0, and we have negative x if x is less than 0. So basically, anytime we have a piecewise graph, there's a risk. There's a risk that we're going to have an issue like this, where we have a corner or a jump discontinuity or something like that. So now, why is this not differentiable? Well, so imagine we drew a tangent line on the left side. No matter where we are, the tangent line is literally going to be on top of the black line because it's not curving, it's not changing, the rate of increase is constant, right? Remember that the tangent line is going to have the slope of a point on the graph. And so over here, no matter what point we're at, the slope is the same, right? And it actually is going to have a -1 slope, right? Here it is, -1x. So that's why the slope there is -1. Now on the right side, no matter where you are, the tangent line will always have a slope of 1. So here, let's actually put that down. Now how do I write that? So we would say on the left side, the slope, or f prime of x, is always -1. But on the right side, the slope or the derivative is always going to be +1. Okay? And so we cannot find a derivative at 0. So it's not differentiable at x equals 0 because the slope is -1, -1, -1, and then we get to 0 all of a sudden. And there's no, it's like an abrupt change, right? Things need to gradually get there, or at least, hit every value in order to get to 0. So for example, it cannot jump from -1 to +1 without hitting all the other values in between, right? And so for that reason, we have a point right here at x equals 0. It's not differentiable there because it does not make sense to find a tangent line there, okay? Second case is actually similar to this one. We call them a cusp. The argument is going to be pretty much the same, and so you may not be familiar with the x to the 2/3 graph, but think of this as x to the 1/3 squared, or in other words, cube root of x squared. Lots of different ways to think about this graph. I know that the cube root graph looks roughly something like this, right? And now if we square everything, it just kind of increases it on the right side, and then on the left side, instead of being negative, it actually flips it over and makes it look something like this. And so right there, at the same location as above, at x equals 0, not differentiable. Okay, and you can see it. So if I were to draw tangent lines, right? So here, I'm pretty flat, so the slope for that tangent line is 0. Here, it's starting to kind of turn around, so it's now negative. Here, tangent line looks something like that. As we get close to 0, on the left-hand side, okay, my slope is almost -infinity. Okay, because think if my pen is the tangent line, as we cruise along the graph, the tangent line starts to turn, right? And eventually it gets so close to being vertical, right? So maybe it starts as an almost 0 slope, -1 slope, -2 slope, -3 slope, and eventually it gets really, really close to -infinity for the slope on that side. And over on this side, it's the same argument, just the other direction. Positive slope, kind of flat, little steeper, little steeper, little steeper. And as I get close to 0, okay, over here on the right side, we get close to positive infinity, okay? You cannot change from a really, really negative slope to a really, really positive slope for the same reason that we can't just jump from -1 to +1 as our slope, okay? So again, hopefully you're seeing the picture here that if you're imagining the tangent lines for these graphs, you can start to visualize why it does not make sense to have a derivative there. Okay, so anything sharp, really, okay? Anything sharp, a corner, a cusp, if you can just remember that visually, then you'll be in good shape. All right? The third case is a little bit less obvious. And that would be something where tangent lines are vertical. And so if I take a look at f of x equals just the cube root of x, the one we just talked about before we squared it. Okay, on this side we get something that looks like that. On this side we get something that looks like this. So we get this little snake, right? And so again, imagine tangent lines, because the slopes, those are the derivatives, right? The slopes of the tangent lines, that's what the derivatives are. Here's a tangent line, pretty flat. Here's another one. Here's another one, right? As I get close to 0, the tangent line is going to become vertical. And you can see it on this side as well. Pretty flat, a little steeper, and eventually when I get to 0, I get a tangent line that is vertical there. Okay, so the tangent line is vertical at x equals 0. So the derivative is approaching infinity there. And so for that reason, we have a not differentiable at x equals 0 again. Okay, so those are 3 basic cases. Anything sharp, so corners or cusps, which is more exaggerated, or something like this where the slope of the tangent line would be, the tangent line becomes vertical, in other words, having infinite slope. That's another reason why we don't have a derivative there. Okay, so those are the basic not differentiable cases. Now we're going to explore, all right, so what can we do about that? How can we make certain functions actually have derivatives or be differentiable? So here's the first example. We'll do a couple. First, let's just verify, is f of x equal to the piecewise function x squared plus 1 if x is less than or equal to 2, and let's say 4x minus 3 if x is greater than 2. Let's figure out, are we going to be differentiable at this location, at x equals 2? Well, first, we want to make sure that we're on the same point, right? So at x equals 2, we have 2 squared plus 1, and that equals 5, which definitely equals, so this is the left side of the graph. This is the right side. If I plug in 2 there, 4 times 2 minus 3. Okay, so we definitely don't have any discontinuity, right? So now the next piece is this. You want to make sure that the slopes or the derivatives have to agree at x equals 2. In other words, if on one, kind of like this example up here, if I look at the derivative on the left, I get negative 1. On the right, I get positive 1. Those don't agree at 0, and so I cannot have a derivative there. Now, we're going to kind of do the same thing here. And so first, we're going to go ahead and find the derivative of the 2 pieces there. So to find the derivative, f prime of x, remember the power rule, right? This 2 just comes out in front. You get 2x. And then 1, if you take the derivative of 1, that's going to be 0. So we get just 2x there. Here, 4x minus 3, again, the power there is just a 1, so that goes out in front, multiplies the 4, still going to be 4. Decrease this exponent, so now it's x to the 0, so we just get 4. Same thing as we did up here, this exponent becomes x to the first. Okay, and now negative 3, the derivative for negative 3 is going to be 0, and so here's our new piecewise graph. And so how do I check? Well, let's see. On the left, if I do 2 times 2, I have that 4 equals f prime of x. On the right, I have literally just 4, right? And so since these are the same, okay, we can say that it's differentiable at x equals 2. Okay, So first, make sure that we are in agreement at the location of the points. That's what we did up here. Okay, we saw that at x equals 2, regardless of which piece of the graph you were on, you're going to be at y equals 5. Next, we want to check the derivatives for each piece of the graph. The first derivative is 2x, the second one is 4. So on the left side, if you plug 2 in, you get 4. On the right side, since it's exactly equal to 4, we have matching derivatives or matching slopes of tangent lines, which means that we have differentiability there. All right, we're going to do one more example. We're going to step things up a little bit and work backwards. So let's go ahead and find A and B so that f of x is continuous and differentiable. And so here's the function. F of x is going to equal x squared minus b times x. And that's if x is less than or equal to 1. And let's do ax squared plus 1 if x is greater than 1. Okay, so if you did not see this differentiable piece, this is just like the problems from the previous quiz, actually. If we want to make sure that these are continuous, then these two have to have the same value or be equal to each other at this location at x equals 1. So that's the first thing we're going to do. So for continuity, we check at x equals 1, okay? We take the first one, we have 1 squared minus b times 1, and that has to equal, if I plug 1 into the second function, it'd be a times 1 squared plus 1. Okay, if I clean that up, I get 1 minus b equals a plus 1. Now, clearly I can't do anything with that because I have two variables and I can't solve. Now, this is where the differentiable part comes in, right? In order for this graph or for this function to be differentiable, the derivatives, right? F prime of x must agree at x equals 1. So let's find f prime of x first. So finding the derivative, again, it's just the power rule. Bring this exponent out in front, make it 2x, and then this decreases by 1, so it's just x to the first. If I take the derivative of the second term, bx, right? This coefficient is just there. This 1 comes out and doesn't do anything there, so it's just going to be minus b. That goes to the x to the 0, so the x kind of disappears there. And the second part, same idea. That'll be 2ax. And again, it's the same location. X is less than or equal to 1, and x is greater than 1. So now that I know what f prime of x equals, at x equals 1, I'm going to take this, plug it in, so it'd be 2 times 1 minus b, and that has to equal this other one, which is 2 times a times 1. Let's clean that up a bit. We get 2 minus b equals 2a. All right. And so now we have a system of equations. We have a system of equations. Two equations, two unknowns. We can now solve them. In fact, I'm going to rewrite these as the usual format. Maybe that'll be more helpful. I can subtract 1 on both sides, and I can add b to the left, or to the right. And so my first equation is going to be 0 equals a plus b, right? So I'm just moving the negative b to the other side, canceling out the 1's. So here's my first equation. my second equation, I'm just going to add the b over as well. So I get 2 equals 2a plus b. And now you can either substitute. So if you want, you can get a alone and then plug it in. Or if you prefer to eliminate, you can eliminate. I like elimination. So I'm just going to subtract 0 minus 2 is negative 2. A minus 2a is going to be negative a. B minus b cancels out. That's why I was subtracting in the first place. I know that a has to be 2. Okay, and now it's pretty obvious. If a is 2 and I add b to it, b has to be negative 2 in order for this first equation to be true. Now, if you were to plug a in here, right, you can still do it that way. You get negative 2 as well. All right, so that is a little bit about differentiability. The last thing that we should make a note of, and this is kind of important, is that if f is differentiable, then f of x must be continuous. Okay? All right. Can't have differentiability without continuity. So if it's differentiable, then it means it was continuous as well. All right, so that wraps up today's lesson. We'll see you next time.